this BS seminar, and I'm very happy to introduce Daniel Brandenburg from the Ohio State University. Daniel got his PhD in 2018 from Rice University, and he came to Brookhaven right after that as a postdoc and worked in STAR from 2018 to last year, and now he is an assistant professor at the Ohio State University. He just started early this year. So Daniel has been, I would say, a very rising star in the field. He also got quite a few awards. For example, in 2019, he presented his results at QuackMatter and was awarded the Nuclear Physics A Young Scientist Award. In 2020, he was awarded the Goldhaber Distinguished Fellowship from Brookhaven, and last year he was the Brahmanic Regional Award for Young Scientist, and I was very happy. Actually, I was attending the ceremony with him, and he has published, I will say, quite a few analysis and very important results in the last few years, and we will hear what he is going to say. And Daniel, please go ahead.
So thank you for that nice introduction, Jungbu, and thank you again for this invitation. So I hope something I say will interest all of you. What I titled my talk is From QED to QCD, Discoveries and Applications with Polarized Photons. And so what I want to do is go through and really talk about what I mean there, and walk you through this journey where we started with some interesting phenomena in QED. And what we found over the last few years is that by making new and interesting discoveries in QED, we can actually really gain new insight in QCD and in high energy nuclear experiment. So, okay, so the outline of my talk is, first I'll go through a quick introduction, and then really the talk is split into two parts. So I'll talk about the discovery of the Breit-Wheeler process, because this is really what lays the foundation for the applications that I'll talk about. And then in the second part of the talk, I'll go through really this new application in high energy nuclear physics and the discovery of this thing called entanglement enabled quantum interference. So that's going to be the second part of the talk. And then I'll end with a summary. And depending on how I am on time, I'll discuss a couple more applications, or we can come back to those in the Q&A. So the work that I'll go through in this talk it's really the culmination of quite a few different papers, both from the STAR collaboration and from several of us doing phenomenological work really over the last 5 or 6 years. And so it's really been, like I said, a journey from focusing on a few interesting phenomena in QED. And what I hope to show you is that we've connected this to some really new and important aspects in our field, in high energy nuclear physics. So one of the most recent parts of this is, to our knowledge, the first paper from our field published in Science Advances, which is part of the Science Journal, and Science Advances is their open access part of their journal family. And we were very pleased to have our article actually featured on the website. So it was on the front page of Science Advances. And we did our best to come up with a somewhat artistic and interesting okay, sorry, I got to move these windows around. So we tried to come up with an interesting and artistic figure to go with it. Okay, so that's my introduction. So let's go ahead and get started. So like I said, to start with, I want to just mention a few aspects of QED. And to some degree, it's helpful to remember a few of the changes that brought us from classical electrodynamics to quantum electrodynamics. And so, while the birth of quantum mechanics really ushered in an entire, shift in paradigm, not just for electrodynamics, but really for all of physics, there's three important discoveries that I want to emphasize here. So the first, and something that's known as one of the most famous equations in all of physics, is Einstein's energy mass equivalence, right? So you have E equals mc squared, which tells us that there's this kind of two-way street between energy and matter. So you can take energy and convert it into matter. You can take matter and convert it into energy. At the same time, you have Heisenberg's uncertainty principle. So I think we're most familiar with the form in terms of position and momentum. But you can also formulate it in terms of the energy and the time of a process. So this tells you that if you operate in a process at very, very short timescales, you introduce essentially an uncertainty on the energy that takes place in that process. And then the third component was that in the late 1920s, Dirac predicted these negative electron energy states. And for just a couple of years, these energy states weren't, their physical meaning wasn't completely understood until Anderson discovered the positron. And so with the discovery of the positron, we realized that there's this symmetry between matter and antimatter. And this is important because if you put these three discoveries together, you can realize vacuum fluctuations. So if you have something like a photon, which is uncharged, and it has a certain set of quantum numbers, if you have only an electron, you can't do anything. This photon can't fluctuate into a single electron. But with the discovery of the positron, you can now have all of the quantum numbers conserved, and the photon can momentarily fluctuate into an electron-positron pair, again, at very short time scales for the energy to work out. And then it will fluctuate back into more like a bare photon. So this idea of vacuum fluctuations is important because it allows basically a pathway or a bridge for photons to interact with matter. And this is really a core understanding in quantum mechanics. It allows us to write out the fundamental interactions between light and matter. And of course, over the years, one of the best ways to describe processes is using Feynman diagrams. So one of the things I think is interesting is that right here on one slide, we can actually list essentially all of the fundamental or tree level interactions between light and matter, according to quantum electrodynamics. So if we start here in the top left, this is a Feynman diagram, which shows a real photon and an electron interacting in the presence of an electromagnetic field or a virtual photon. And this is a Feynman diagram meant to depict the photoelectric effect. So that was first predicted in the late 1800s. We have other processes like Brim-Strahlung and Compton scattering predicted over the next 20 or so years. And the interesting thing is that all of these fundamental processes in QED, even before QED was fully formed, all of these processes were predicted, and in most cases, they were observed within the next few years. So the experimental confirmation came quite quickly after the original theoretical prediction. And I'll draw your attention, for instance, to the Dirac annihilation process. This was predicted in 1934. It's the case in which you have an electron and a positron annihilate and produce two photons. This process has been measured to such high precision that QED is often known as one of the most precise theories in all of physics. However, there's one final process here. It's it's the time inverse of the annihilation process. So now instead of an electron-positron pair annihilating into two photons, you have two photons in the initial state colliding to produce an electron-positron pair. This is known as the Breit-Wheeler pair production process. And like the rest of these processes, it was predicted in the early days. So in 1934, again, at this time in the birth of quantum mechanics, the unique thing about this process is that unlike all the others, it remained without an experimental confirmation for several decades, for almost 90 years. So if we look at this process with a little bit more detail, we can start to understand why it's a bit more challenging. So the Breit-Wheeler process consists of the collision of two real photons. And if we express this in terms of the Feynman diagrams, we can think of it in terms of these two Feynman diagrams, which will interfere due to the ambiguity of the source of the first and the second photons. Now, one of the first things that we can mention, as I mentioned a few slides ago, is that this is a nonlinear effect. So in classical electromagnetism, it's a linear theory, which means that superposition is a manifest property of that theory. So if we think of that in terms of photons, it would mean that photons travel through each other and they don't interact. However, as we've mentioned, in the quantum theory of electrodynamics, photons can fluctuate into an electron-positron pair, and that means that we can actually have interactions between photons mediated by these vacuum fluctuations. At lowest order, like I said, it's given by these two Feynman diagrams. It involves the collision of real photons, and it's the only one of these tree-level processes that was not observed, like I said, quickly after, and in fact was not observed for more than 80 years. Now, the interesting thing is that Breit and Wheeler, they really recognized the difficulty in observing this process, and they commented in their 1934 paper that it's hopeless to try to observe this pair formation in the laboratory with two beams of X-rays or gamma rays because of the smallness of the cross-section and the insufficiently large available densities of quanta. So what does that mean exactly? It means that the photon-photon interaction cross-section is quite small. So you have to get these photons really close together, and you need a large enough source of photons, not only to get them close together, but these photons have to be extremely high energy to cross this energy threshold to produce an electron-positron pair. They weren't completely without hope, though, because they took note of the work of Weizsacker and Williams, and they noted that large nuclear electric fields can lead to large enough densities of quanta to actually increase this effect to an observable amount. And so they already recognized back in the 1930s, many decades before heavy ion collisions would take place, that this is the ideal situation to realize this process. And so I think many of you, of course, are familiar, but just as a quick recap, we can achieve extremely strong electromagnetic fields in heavy ion collisions. And so if we want to study the electromagnetic fields directly, so-called ultra-peripheral collisions are the most ideal setup. In these ultra-peripheral collisions, we have so-called collisions where the nuclei actually pass far enough apart that the nuclei themselves don't overlap, and therefore, because the strong force is a short-range force, we don't have any strong interaction. However, because the electromagnetic force is long-range, we can still have interactions through the electromagnetic force or through photons. And the description of this is given to us by the Weizsacker-Williams equivalent photon approximation. And essentially what it does is it allows us to take a semi-classical electromagnetic field and express the photon distribution that field carries. So it's kind of this connection between the semi-classical description of the field and the quantum description of the field in terms of the flux of photons. Now, in heavy ion collisions, we have a really interesting and extreme case in that these nuclei are heavy enough, they have a large enough Z, so a large enough charge, that Z times alpha is relatively large. It's close enough to 1 that essentially what this means is that you have a high photon density and the probability of having multiple couplings so that you can achieve a process like this two-photon interaction starts to become non-negligible. And to give you an idea, if you're unfamiliar, these fields are so strong that in fact, they produce the strongest, though very short-lived, electromagnetic fields in the universe. So to put that in perspective, for a very short period of time when these fields are overlapping, a small region of space is experiencing a magnetic field on the order of 10 to the 15, 10 to the 16 Tesla. So this is, for instance, a few orders of magnitude stronger than even the strongest electromagnetic fields produced around like pulsars, for instance, which would come in at 10 to the 11, maybe 10 to the 12 Tesla. So heavy ion collisions really give us this unique and extreme laboratory for testing QED under extreme conditions. Now, coming back to the Breit-Wheeler process, there's a couple of different ways that you could experimentally go about trying to identify the Breit-Wheeler process in heavy ion collisions. And in other talks and in some of our papers, we really go through, detail by detail, point by point, all of the different features that you would expect for the Breit-Wheeler process in heavy ion collisions, because you have to distinguish it from the plethora of interactions that take place with virtual photons. However, there's really one aspect of the interaction which is extremely unique to the Breit-Wheeler process, because it gives you direct access to the wave function of the interfering or the colliding photons. And because of that, it's really the most, the strongest measurement that you can make to identify this process. And that has to do with the polarization or the spin components of the colliding photons. So what I want to do is draw your attention to this figure in the top left first. So this is a diagram of these heavy nuclei in the transverse plane. So one of the nuclei is going into the screen and the other is coming out of the screen. And they produce these highly Lorentz contracted electromagnetic fields, where the electric field is radial with respect to the source, and the magnetic field circles around the source. Now, this configuration is quite specific and important, because what it means is that at any given location in space, the configuration of the electromagnetic field and the direction of motion correspond to what you would expect for a linearly polarized electromagnetic wave. So it's this combination of the electric field and magnetic field perpendicular and mutually perpendicular to the direction of motion. So what that means is that if you can imagine, as these nuclei are passing, you don't know exactly where these photons from the fields might interact, but you can have a photon from the field of nucleus 1 interact with a photon from the field of nucleus 2, and there's a probability of those interacting at all different regions in space. Now, they're most likely to interact where the overlap in the fields is strongest. So that's kind of roughly this area between the two nuclei. But there's also a probability for them to interact at other locations in space. And the real interesting point that I want to point out is that the different spatial configurations lead to different angles between these photon polarizations. So again, the photon polarization direction is given by the electric field direction. So in this case, the photon polarizations point nearly anti-parallel. So they're essentially back-to-back. Whereas if the photons collide up here, the polarization is at roughly 90 degrees. So you might think, okay, interesting, but so what? Well, it turns out that really from the very beginning, one of the key features that separates the Breit-Wheeler process from other processes is that the cross-section should depend on this polarization So photon-photon polarization angle. So whether the photons interact in a parallel or anti-parallel configuration versus a perpendicular configuration, it actually changes the cross-section of the Breit-Wheeler process, and it changes the differential cross-section through a process related to vacuum birefringence, which was first predicted in the 1930s and worked on more by one of Wheeler's students in the 1950s. So it turns out that the differential cross-section, so as a function of the angle, the azimuthal angle, will have these modulations due to the fact that you have these different photon-photon polarization interactions. And let me explain a little bit as to how that arises. So if we switch over here to the right side of the slide, the idea here is that if you have a general density matrix for these two photons interacting, you have, for instance, a positive spin projection, a zero spin projection, and a negative spin projection. And then again, on the x-axis, you have a negative spin projection, zero, and positive. So that's the general density matrix for this two photon system because the photons are spin one objects. However, because real photons are massless, the spin zero projection is forbidden. And what this means is that when you form this two photon state, you're really only able to form certain spin projections. And specifically, you can form these JP states of either 2 plus minus or 0 plus minus. So what that means is the spin projections can cancel and form a zero state, or they can add together and form a state with total spin projection of 2. And this is the interesting case because now you can think of it as a composite system which has spin 2 and then decays to an electron-positron pair. Because the electron-positron pair tend to be produced in the singlet state, these two units of spin have to be encoded into the orbital angular momentum of this electron-positron pair. And what that means is that it actually is observable in terms of the angle between the pair momentum and one of the daughters. So what that means is that when you have this spin 2 object decay, it actually will preferentially decay the positron in the direction of the pair momentum, or off to 90 degrees. So depending on the total spin in the system, you have these modulations where the decay is preferentially oriented with the momentum of the pair. So that's the real key experimental fact here. And again, it's related to this photon-photon polarization. And so in 2021, we published a measurement of this in Physical Review Letters, and it looks like this over here on the right. So we looked at this in ultra-peripheral collisions. So this case where the nuclei don't actually have a strong interaction. And we also looked at it at smaller impact parameters where these nuclei just barely overlap. And so what we did is we compared this measurement to the process. So the process with all of the kinematics, all of these cross-section effects, but not this differential effect, which is due to the photon polarization. And what you can see is that that produces a cross-section which is essentially flat in this phi angle. So that's this angle between the pair momentum and the positron. However, if you do this calculation in the full lowest order QED or in other models that take into account this photon polarization effect, what you see is this strong cosine 4 phi modulation. And you can see that the data agrees almost perfectly with the QED and the super chic prediction, which takes this effect into account. And same thing, at these smaller impact parameters, we expect this modulation to get even a little bit stronger. And we find that the data, in fact, does show that and agrees quite well with the QED prediction. So this measurement is not only a strong measurement in the sense that it proves that we're observing the Breit-Wheeler process, but from a much more practical standpoint, it proves that we have access to the photon polarization for the very first time in heavy ion collisions. And I want to emphasize that this is an analogy to something that we've been working towards in the QCD side of things, because gaining access to this photon polarization essentially allows us access to the full photon Wigner distribution. So that means the full phase space distribution of the photon's momentum and its correlations between its distribution in space and its spin. So this is an analogy in the sense that a huge goal in nuclear physics, in high energy nuclear physics, is to obtain exactly this kind of measurement, but for the gluons inside a nucleus. And so this really paves the way, in some sense, for the progress that we hope to make over the next 10 or 20 years. So we published this in 2021, and it's been received quite well, both in terms of the attention from media. So for instance, there was some journalism that picked this up, and Inverse magazine specifically picked it up as part of a kind of a celebration of all the accomplishments of Einstein. And with that, they had some quite nice illustrations, as you can see. Now, I think the appeal to the kind of general population is quite nice, but I think one of the things that's been most encouraging to me is that this measurement and this idea that you can look at the Breit-Wheeler process and vacuum birefringence through these differential processes, these differential modulations, has really been a source of inspiration in the strong QED, in the field of strong field QED, and specifically there's actually quite a large experimental community that's trying to achieve the Breit-Wheeler process and vacuum birefringence with laser-based experiments. And so I just pulled a handful of citations from our paper from this kind of strong field QED community. And what you can see is they've really taken our work and they've recognized that, yes, this is interesting and important in heavy ion collisions, but actually we can use these same ideas in these laser-driven experiments, and it really appears to be having quite a large impact even in that other community. And so that's a really exciting thing to see happen. Okay, so with that, I want to move on to a few applications, and then we'll switch gears and talk about applications in QCD. So since this is a RIC BES seminar, I wanted to at least touch on some of the connections to the beam energy scan. We have a student, so Zhangbu and I have worked with Xiaofang, who's a PhD student at Shandong University. She's a really excellent student that has taken this early work and has extended it in a couple of different directions. So as I've described to you over the last few slides, the Breit-Wheeler process is sensitive to the spatial configuration and the strength of these electromagnetic fields. And what that does is it actually means that we are sensitive to the actual form factor or the charge distribution within these heavy nuclei. It's not super straightforward to get to that information, but it is possible. And Xiaofang has done quite a bit of work on this to extract this charge distribution from these in situ colliding heavy nuclei. And so if you look at these plots here in the middle, what it shows is kind of a 2-parameter search where we take a Wood-Saxon distribution, which has a radius and a skin depth, and we compare that to the star data with the QED calculations kind of as the bridge. So we start out with a Wood-Saxon, we compute via QED all of the Breit-Wheeler observables, and then we do a chi-squared minimization to try to see what charge distribution is consistent with the data. And what you can see here is that we have measurements at 200 GeV from ultra-peripheral collisions and from these very peripheral min-bias collisions. And they really do show different sensitivity to these parameters. And when you combine them, you get quite strong constraints on the actual charge radius and skin depth. we have this separated for different types of ultra-peripheral collisions because there's some difficulty in modeling the exact impact parameter that goes into these different ultra-peripheral collisions. So it has to do with the fact that ultra-peripheral collisions that pass close by tend to have lots of neutrons in the forward and backward direction, whereas ultra-peripheral collisions that pass far apart tend to have only a few neutrons. And so if we try to separate it by these two types of events, we gain some understanding. We can also use a parameterized approach, which tries to take it all into account at once. In that case, the constraints are a little bit less strong, but it shows you kind of the different sensitivity that we have. So this is an interesting idea, and it's something that we'll be able to build upon with 100 or even 1,000 times more precision with the data that STAR will collect in the next 2 or 3 years. I think one of the other interesting things that Xiaofeng has pioneered, though, is how do you look at this process as you go to lower and lower energies? There's actually some interesting aspects here, because as you go to lower energies, these electromagnetic fields become less Lorentz contracted. So they spread out in the longitudinal direction. And it kind of puts this equivalent photon approximation on shaky ground, because the equivalent photon approximation really works when you have these highly Lorentz contracted fields. And so you expect a divergence of the photon flux. And Xiaofeng has actually done quite a bit of work, both from the theoretical side to understand this through QED calculations, UPC triggers in the beam energy scan data. So what she actually developed is a technique for looking at the very peripheral collisions and extracting these measurements from, for instance, the 80 to 100% peripheral collisions. And so what you can see here is the invariant mass distribution of the Breit-Wheeler electron-positron pair compared to the QED calculation. And for comparison, we have the 200 GeV result also in 80 to 100. So Xiaofeng has carried out quite a few measurements like this, and it's allowed us to look for the very first time at the energy dependence of these processes. And specifically, one of the things we expect is that as these fields begin to spread out, you actually have a broadening of the transverse momentum distribution of this electron-positron pair. And so what we can see here is that at 200 GeV, we have a lower or a more compact PT distribution, and then it begins to spread out as you go to these lower beam energies. Now, the statistical and systematic uncertainty here are still quite large, just due to the limited, mostly due to the limited statistics. The interesting thing here, though, is that these data are all systematically above the QED prediction, which is at least qualitatively what you would expect if you had lifetime electromagnetic field effects that were adding some additional bending and spreading out the momentum distribution of these produced pairs. So Xiaofeng has a paper that she's working on that goes into detail about all this and how this may be connected to a long lifetime of the electromagnetic field in heavy ion collisions. So let me go to one final application for the Breit-Wheeler process, and then we'll move on to the final topic of the talk. So as I mentioned a few slides back, the identification of the Breit-Wheeler process is really based on this idea that the photon spin or the photon polarization is unique for real photons. So a few slides back, I showed you that for 2 real photons, the 0 components are not allowed. And it's for that reason that you end up with just these total spin 2 or total spin projection of 0, which leads to this characteristic cosine 4 phi modulation. However, we have such a large amount of energy in these electromagnetic fields that in principle, the fields could be quantized directly into a dark photon. So a dark photon is a mediator of this hidden sector in these models that include something like a QED interaction between dark matter. And in essentially all of these models, the dark photon has a non-zero mass. And so if you have an interaction like this, where you have one real photon from one nucleus interact with a dark photon manifest from the field of the other nucleus, you actually change this density matrix. And so now the real photon still has to have spin projections of plus or minus, but because this dark photon actually has a non-zero mass, it can allow this zero spin projection, and that actually modifies the modulation that you expect in the final state. So as you can see down here, this is the star data, and in blue is the QED prediction for the Breit-Wheeler process. So that's 2 real photons. And the idea here is that if you have a dark photon taking place in this interaction, for one, you'll have an increase in the cross-section because you have an additional process. But what's even more sensitive is that this dark photon, like I said, because it can be in this spin zero projection, will lead to a cosine 2 delta phi modulation, which is quite distinct from the cosine 4 phi modulation. And so already with the existing star data, we've been able to apply this idea. So basically what we can do is we can set limits on this cosine 2 phi modulation. And by doing that, we can actually put limits on the dark photon mass and coupling to the standard model. So that's the limit that we can currently set in this shaded red region. And with the data that we expect to collect over the next 3 years with STAR, we actually expect to be able to set much stronger limits that are actually sensitive in regions that no other experiments are expected to be sensitive. So we're really excited about this new application. And I want to point out that this is work that was carried out by a high school student that was a BNL summer high school student, and with Nicole Lewis, who's a postdoc at Brookhaven. So we really had a very successful kind of outreach program with this high school student, and this paper was recently submitted to Physical Review Research. Okay, so let's change gears here. Maybe I can stop for any quick questions. Okay, hearing none, let's go ahead and go forward.
Daniel, it's okay. We have a discussion session at the end. So I'm monitoring the chat window. If anyone raise hands or put anything on the chat, I will let you know.
Okay, very good. Okay, so we went through the Breit-Wheeler process, and the real point that I wanted to emphasize is this access to the photon polarization. And so now we want to switch gears and really talk about some core concepts in nuclear physics and in quantum chromodynamics. And what I hope to show you is that this discovery in QED really has some impacts and allows us to do new things in high energy nuclear physics. So let's give a quick motivation here. So as I mentioned earlier, one of the things that we want to do is we want to be able to perform tomography of the nucleon and the nucleus. So that means we want to understand the distribution of matter and of the force carrying particles within nucleons and nuclei to better understand their dynamics and their emergent properties. And there are connections over the years. We've realized that there are connections really across many different scales in physics. So for instance, astrophysics has recently made this connection where they can actually place constraints on the equation of state of nuclear physics. So for instance, there are nicer X-ray telescope measurements that are actually able to look out in the distant universe and measure pulsar radii to better than 10%. To me, that's just an incredible measurement, because these pulsars are only on the order of a few, around 10 kilometers, about the size of Manhattan. So the fact that they can measure these radii to such precision is really incredible. And over the last several years, we've moved into a new age of multi-messenger astronomy with the advent of gravitational wave observers like LIGO, which allow us to actually look at the deformation of these massive objects as they inspiral. So these types of measurements are really giving new constraints on the equation of state of nuclear matter. But there's still quite a few open questions, even if we just think about the astrophysical side. So for instance, there are questions as to whether there's a non-zero strangeness component in the neutron star interior, and whether or not there's a phase transition that takes place in the core of these stars, which might soften the equation of state and impact the radii of these stars and their deformability. Now, a few years ago in PRL, the PREX-2 experiment produced a very precise measurement of the neutron skin of lead. So this is the difference, the root mean square difference between the neutron distribution and the proton distribution, or the charge distribution within the nucleus. And what they found was that it was a relatively large neutron skin of about 0.3 Fermi. Now, I just want to point out that they actually don't measure this directly. They measure it through this thing called APV, which is a parity violating asymmetry. And if you look up here in the top left plot, essentially what they do is they measure this APV value. So that's their actual measurement with its uncertainties. And then by using certain theoretical and phenomenological input, they can translate that into the weak radius and the neutron skin of the observed nucleus, so 208 lead. But it's really important to keep in mind that this is not a direct measurement. It takes place through this kind of translation layer. And like I said, they find this neutron skin, which is, 0.3 Fermi might sound small, but it's actually a bit larger than is expected for lead. And if we compare this with the constraints on the equation of state from these X-ray measurements and from the gravitational wave observers, what we find is that there's actually pretty good agreement between PREX. So if you look on this plot, the allowed region for PREX is this blue region. And the allowed region from the X-ray measurement is the vertical region between these pink measurements. So you can see there's a region here that is in good agreement between these two types of measurements. So that's okay, that's great. We have two completely different measurements. They seem to agree. However, if you take the absolute lowest value of this deformability parameter that the PREX-2 neutron skin allows, it's this lower dashed line here. And like I said, that's all in good agreement with the X-ray measurement. However, these recent gravitational wave observations have produced a fairly precise measurement of this deformability parameter, and they find something much lower. It only really touches the lowest part of the PREX line at the 1 or 2 sigma level. So the tension is not super strong, but there is some tension here. And as I mentioned, it's actually interesting because the PREX measurement, like I said, it has to go through this kind of translation layer. And there's actually another paper in PRL, which takes a different approach to converting this APV value to the neutron skin. And they find a value which is a little bit smaller. So it's about 30% smaller, which would put them down here. It may relieve some of this tension. But I think what I want to point out here is that there's some really interesting physics that we have access to here. There may or may not be tension between high energy nuclear physics and the astrophysics, but really what we need to pin this down are more precise measurements of the neutron skin. So that's the motivation for the next few slides. And with that, I want to introduce a quick puzzle as to why we haven't been able to make this measurement in the past. So we've known for decades, since DAISY and Hera, that using photons, we can investigate the hadronic structure of the nucleon and nuclei. So for instance, at Hera, there was an EP collider. You can have a photonuclear interaction where you have a virtual photon from the electron beam fluctuate into a quark-antiquark pair and then interact through gluons with the nucleon. And you can produce a vector meson state because of the quantum numbers of the photon. And that vector meson can decay to various different particles. And then by observing this, you can learn information about the structure of the nucleon or the nucleus that you collided with. Now, Starr knew that this was an important measurement, and so from the very beginning of the days of Rick, Starr made this a priority to measure. And so photon-Pomeron interactions were one of the first measurements in the first few years when Starr turned on. And they made these nice measurements of the ρ0 meson decaying to pi plus pi minus, and they really investigated the different interfering components to this amplitude. So you have the ρ itself, you have direct pi plus pi minus contribution, and then you have this interesting interference pattern which comes from production of the omega as well. And so this measurement came out in 2002, like I said, very quickly after Rick began running. And since then, there have been detailed measurements of the diffractive structure of this process. So if you look at the T distribution, so the Mandelstam T, which is approximately the PT squared of the pi plus pi minus pair, you see this beautiful diffractive pattern. And we know from Fourier analysis that this diffractive pattern is related to the spatial distribution, for instance, of the gluons within the nucleus. And this idea has been around really since the first measurements. And other measurements have been made at the LHC since then. So for instance, Alice has made measurements of J psi and of the ρ. So we have all these measurements. So you're probably thinking, okay, so what's the problem? The problem is that if you actually do the Fourier transformation on this, you take this beautiful diffractive pattern and you ask, what is the effective radius of the quarks and gluons that produce this distribution? You find for gold an effective radius of about 8 Fermi, and for lead an effective radius also of about 8 Fermi. If you compare this to the charge distribution or the charge radius, which we know to extremely high precision from low energy scattering measurements, this is just way too big. 8 Fermi is too big to be explained even by energy dependent effects or saturation effects. It's really just too big. And so for many years, we've had these measurements, but we've really refrained from making a strong statement about the nuclear geometry or the gluon distribution because these numbers just really didn't make sense. So the question is, what's new after 20 years and how can we resolve this puzzle? And again, it really comes back to this idea that we now have access to the photon polarization. So this is just a reminder slide from the Breit-Wheeler process. In that case, we had a photon from each field, and it could interact in different places in space, and that led to this difference in the photon-photon polarization angle. In that case, we had 2 photons, so we could end up with 2 units of spin. And when those 2 units of spin got encoded into the orbital angular momentum of the E plus E minus, you got a cosine 4 phi modulation in this phi angle, the angle between the momentum of the pair and one of the daughters. So now we can look at this for this photonuclear process, and it's going to be a very similar situation. We have a polarized photon, just one in this case, because we have a photon interacting with a Pomeron. And what we're going to see is that that spin can become encoded in the process in a very similar way. And so with that, that brings me to the next part of the talk, which is the entanglement-enabled quantum interference. And as I just mentioned, the whole point is that we have this access to this polarized.
You have about 10 minutes.
Okay, that's good. So in this case, we have 2 different possibilities. We have a photon which is emitted from the left, travels to the right, and produces a ρ. We have a photon from the right, which travels to the left, produces a ρ and decays. But it turns out that actually we can have both of these things happening simultaneously. And again, the interesting thing here is that the photon polarization is given by the electric field direction. So this photon is polarized in that direction, whereas this photon is polarized in the other direction. Again, we actually can gain sensitivity to the polarization in this process by using exactly the same observable, this phi angle, as we just talked about for the Breit-Wheeler process. Now, again, the difference is that the Pomeron, at least to lowest order, is a spin zero object. So we only expect one unit of spin in the final state. So that's going to give us a cosine 2 phi modulation instead of a cosine 4 phi modulation. And again, this comes from the fact that we have photons polarized in this direction on one part of the amplitude and photons polarized in this direction on the other part of the amplitude. This ends up being very similar to a double slit experiment. I'll go ahead to this slide to save a little time. It's very similar to a double slit experiment in the sense that we have a row produced on one nucleus and a row produced on the other nucleus. But there's one really interesting distinction here, which is that the row lifetime is too short to actually travel and interfere with the other row before it decays. So the row lifetime is so short that they really decay to a pi plus pi minus before they actually have time, even at the speed of light, to interfere with each other. So what this means is that if you do have interference, you have to have the interference taking place between the daughter particles, the pi plus and the pi minus. But traditionally in quantum mechanics, we think of interference taking place only between identical states or indistinguishable states. So this is actually a really strange phenomenon that naively would seem to contradict what we know about interference in quantum mechanics. However, Frank Wilczek's group at MIT has actually been thinking about this even before we did this measurement, and they came up with an interesting experiment that actually could demonstrate interference between distinguishable particles, and our case is actually quite similar. We made this measurement, and so we can look at these photonuclear production of the row, and in fact, we see this very strong cosine 2 delta phi modulation. We looked at it in gold-gold, uranium-uranium, and as a null hypothesis, we looked at it in proton gold, because in that case, you shouldn't have these two different possible configurations, and this interference effect shouldn't be taking place. So in fact, in p gold, we see no interference. In gold-gold and uranium-uranium, we see quite a strong interference. And the strength of the interference is different between gold and uranium, which already gives you a hint that there's some sensitivity to the nuclear geometry. So the interesting thing here is that in order for this interference to take place, there has to be some entanglement in the system. Now, the kind of concept from Frank Wilczek's group is that the row decays, and by virtue of the decay, the pi plus pi minus are entangled. So you have a row at the wave function level over here on the left. It decays to a pi plus pi minus, which are entangled. You have a row over here at the wave function level, decay to a pi plus pi minus, which are entangled. And then these propagate as wave functions, which can interfere. And then because they're entangled, the pi plus can interfere with the pi plus, the pi minus can interfere with the pi minus, and then the entanglement actually essentially translates or transfers that interference from the wave function level to a final state real particle interference between the pi minus and the pi plus because of the fact that they're entangled. This is a pretty interesting phenomenon, and we're still working on all the details here, but that's one possible explanation. Another possible explanation, which is similar to the recent Nobel Prize, is that you have something like an entanglement teleportation. So in the classical case, you produce a pair of particles which are entangled at one place. You create another pair of particles which are entangled at another place. And then by getting these two particles to interact, you can actually cause particle 1 and particle 4 to become entangled. This isn't quite what we have because we're dealing with wave functions. They're not actually real particles at this stage, but maybe there's some parallel to this type of picture. We're actually working with a few theorists to better understand from a theory perspective how this phenomenon can take place. The final thing, which I think is very interesting, is that the entanglement could actually start much earlier in the interaction due to the fact that the photon and the pomeron are each, in a sense, emitted by the quarks, which are the only thing that carry both electric charge and strong charge within the nucleus. So maybe the entanglement starts very early and you start with a highly entangled state. However, we have no experimental measurement to prove that the nucleus is in a highly entangled state, kind of at the beginning of the interaction. We hope to have some new measurements at Quark Matter 23 that should shine some light on this entanglement phenomenon. So, okay, with that, let me end very quickly with kind of the final punchline, which is that we can use this new information, this new and very interesting quantum interference effect, to finally get to a very precise measurement of the neutron skin in heavy ion collisions. So I want to just very briefly tell you what this new technique is. So the idea is that because we have access to the photon polarization, we can, for the first time, separate out these two different configurations. So we have a photon interact with a pomeron. When they interact in a parallel configuration or anti-parallel, the decay modulation will follow the polarization direction. However, the momentum direction is really given by the pomeron because it's what provides the momentum transfer in this interaction. So in a configuration like this, we're going to end up with phi angles of 0 or pi. In the other case, when they meet perpendicular, the polarization follows the photon's direction, but the momentum follows the pomeron, and we end up with phi directions of plus minus pi over 2, so 90 degrees. This is important because it allows us to look at the case when this quantum interference effect is the strongest versus when it's the weakest. So if we look over here on the left, we have these configurations where the photon and the pomeron hit head on, and we can look at this T distribution, just like I showed you from the diffractive pattern earlier on. And if we just do the naive thing and we just try to extract the Wood-Saxon radius directly from this T distribution, we get what I showed you earlier, which is that in this configuration, we have a radius of almost 8 Fermi. For gold, that's really surprisingly large. However, if we look at this other configuration, where the interference effect should be at a minimum, we get a radius which is about a Fermi smaller. And this is really shocking because previous to this, we didn't expect the radius that you observe to depend on anything about the event configuration. This right here proves that there's something going on, and you can't just take this T distribution and directly translate that to a radius because it's changing depending on what kind of events and their configuration that you select. So long story short, what you can do is you can look at this effective radius as a function of the phi angle. So this is basically as a function of the strength of this interference effect. What you find is that when the interference is strongest, you have essentially an image that makes the nucleus look much larger. And when you have the interference effect at a minimum, you're starting to get to the true size and shape of the nucleus. And so what we want to know is what's the size over here at these minima. And that's exactly what we can do with this new tomographic technique. So in this table, I won't go through all of it to save time, we have a comparison of all these different measurements that have been done over the years compared to the charge radius here at the top. As I've told you, in the past, the results have always come out really large because this interference effect was essentially distorting the picture. With this new technique, we can remove all of that distortion and really get to the precise distribution of protons and neutrons within the nucleus and compare that to the charge radius to extract the neutron skin. And I just want to point out the precision that we have here. So our statistical and systematic uncertainty are on the order of 5/100ths of a Fermi. And with the data that we plan to collect in the next few years at STAR, we expect to improve this uncertainty by a factor of 10. So we're really entering the ability to gain precise measurements of these neutron skins. And if you actually extract that for gold and for lead. You find a neutron skin of about 0.2 Fermi for gold and about 0.4 Fermi for uranium. So I'll just go ahead and end with a quick reminder that this is connected to the equation of state. I talked to you earlier about this tension with the lead 208 measurement. On this slide, I just put, here's a look at neutron skins measured from low energy experiments with these gold symbols showing our new measurements for gold and for uranium. The uranium measurement is quite large, and it would kind of potentially support this idea that lead had a large neutron skin. So we're looking forward to more input from theory to try to understand and connect these measurements, these new measurements of gold and uranium, to the equation of state. Maybe we can say something about this tension that the P-Rex2 measurement has raised. This measurement has been really well received, but I'll go ahead and end there so that we have plenty of time for questions. I just want to end with a quick summary. We started out by looking at a pure QED process. We became interested in this because, really because we thought that we may be able to learn something about the electromagnetic fields that are taking place in these heavy ion collisions. When we started that work, we had no idea how much of an impact it would have. By making this discovery of the Breit-Wheeler process and gaining access to the polarization of the photons in these interactions, as I've shown you throughout this talk, we've allowed a huge number of new applications in a type of process that's been studied already for decades. So it's really shed new light on these processes. And then when we applied that to the case of QCD and of these photonuclear interactions, we discovered something very interesting in quantum mechanics, which is that when you have entanglement in a very specific setup, you can actually have interference between distinguishable particles. This is really interesting because it's really a fundamental thing in quantum mechanics, which could have applications in other fields. And we're really excited to see where that will go. And then finally, I think the most specific application is that we've been able to use this technique to measure the neutron skin of gold and lead in heavy ion collisions with a precision that's really competitive with these dedicated experiments. So I didn't go into too much detail, but our precision, our current precision is pretty much comparable with the P-Rex2 measurement, which is a dedicated neutron skin measurement. And with the data that we're going to collect in STAR between now and 2025, we're going to be able to put this uncertainty at the level of about 1/100th of a Fermi. So we're really excited about this. And there's quite a few more applications that I didn't even get to talk about. If you're curious, we can go through those in the Q&A time. And I'll just end by saying thank you to all the different people that I've worked with and to the STAR collaboration for all their support in this work. So with that, thank you.
Thank you, Daniel, for this very exciting talk. So now it's open for questions and comments. I will mention there was a comment in the chat window. Thomas, I think it's related to the neutron star radius. Please go ahead.
Yeah, I don't know. That was maybe needlessly nitpicky. So you said 10% accuracy on the NICER experiment when you first introduced it, but these are 1 sigma error bars, and already the 1 sigma error bars, as you can see, are more like 1.5 kilometers. So the 2 sigma error bars are really quite large. And the same is true for this tidal deformability. I mean, you kind of described it as very accurate, but as you can see, it's only mildly inconsistent with 0, and it could be, 3 times larger than the centroid. So I think the thing that has people excited is the fact that it will eventually become very accurate, but right now it's not.
Yes, I agree with that.
So, but I do have since I'm already speaking, I have a quickie question. I mean, the beauty of P-Rex, of course, is that you measure the neutron skin using a fully controlled probe. I mean, we exactly know how Z's and photon couple to the charge distribution and the weak distribution. But the trouble with all these strongly interacting probes, both in low energy and in high energy, is that you're not exactly sure what operator you're actually measuring. I mean, you don't know whether this is the neutron distribution or some other distribution, do you?
So now you're talking about my measurement.
Right,
Yeah.
radius measurements.
I don't know if there's a slide for that, but I think so in our measurement, what we're doing is we're measuring this coupling to gluons by virtue of the event characteristics and the fact that it's a diffractive event. We can be very confident that we're making an observation through this, two gluon Pomeron state. I think the question that you're bringing up is how do you relate that to either the gluon distribution or the neutron distribution? How do you really connect that to, something related to nuclear structure? And I would say that our claim is that to leading order, this gluon distribution that we measure represents the proton plus neutron distribution. However, I mean, one of the reasons that this is exciting to me is because by measuring this in high energy like this and through this Pomeron interaction, we should, in principle, be sensitive to these energy-dependent effects, for instance, saturation effects that might cause the distribution to swell up and be different from what you would measure at low energy, like you said, through these other measurements. So I think as a first measurement here, we should start by comparing and see if we have any difference between the low energy measurements and the high energy measurements. I think so far we don't see a huge difference between, for instance, gold at these high energies versus what we expect at low energies. So I think that it is to leading order, it is a good description of the proton plus neutron distribution. But I guess I'll defer any, further statement on that. I really hope that there will be additional theoretical input here that helps us to further make this connection. So I hope that at least addresses your question.
Thanks.
Okay, next one is Huitao.
My understanding is there is lots of debates for the size of neutron skin for lead at the low energy nuclear physics side. My question is, for example, if you measure the neutron skin for lead from lead collision in the near future, how can you convince our community and the other community your measurement is more precise than the other one? And the other question is, you can also measure the neutron skin for different collision systems, such as the neutron skin for gold, uranium, zirconium, ruthenium, and so on. If you did such measurements, is there any of such nuclei that has been precisely measured from the nuclear physics set that can provide some reference for us?
Mm-hmm. Yeah, very good question. So let me try to address those one at a time. So I think the first thing I would say is that I tried to point out that the P-Rex2 measurement it's not without any theoretical dependence. It's not without any model dependence. So there is some sense in which there's at least some uncertainty due to how you translate this APV measurement to the neutron skin. I think in our case, we have really very minimal model dependence. Our systematic uncertainty includes the model dependence, which is on the order of 0.05 Fermi. And we actually can improve that with the developments that have already been made since these results came out. But I think the biggest point I'd like to make is that it's a completely different measurement. So we have completely different set of systematic uncertainties and model dependencies. So I think in that sense, combining these two measurements is what's really powerful, because we're approaching it from two very different directions. So I think that's the first part. The second part is you're absolutely right. So if we just think about Rick for a moment, We have data from the isobars, like you mentioned. We even have older data from copper and copper gold collisions. And so we have oxygen as well. So we actually have, one of the strengths of RHIC is that we can collide many different species. And this is a brand new measurement. And you're absolutely right. One of the things that we're excited about in STAR, and we're already mobilizing manpower for, is to repeat these types of measurements in all the different kinds of collision species that we can. So obviously the isobar are a topic of prime interest. And so that's a very high priority. Coming back to lead, I've been very excited by this procedure because exactly as you mentioned, we should be able to make a measurement like this in lead-lead collisions. And that will provide at least an apples to apples comparison in the sense that we have lead-lead neutron skin measured at low energy from P-Rex, for instance, and then we'll have it hopefully from heavy ion collisions. Now, again, there may be some energy dependent effects that we need to think about, but from my understanding, and maybe the theorists that are online can correct me, there's essentially no case where we would expect the neutron skin to get smaller with energy. As far as I understand, essentially all the effects would cause the neutron skin to grow. So if we have a very precise measurement of the lead neutron skin in heavy ion collisions, we can compare that to these low energy measurements. If we find that the P-Rex measurement is significantly larger, 30% larger than what we measure in heavy ion collisions, I think that would be a very strong statement. Because like I said, the energy dependent effects should make the neutron skin we measure larger, not smaller. I'm very excited about this. However, it's actually a very challenging measurement for most of the LHC experiments. So I'm actually investigating which of the experiments can do this. Unfortunately, we've never taken lead data at RHIC. So it really has to be done at the LHC. And it's not trivial, but I think at least one or two of the experiments could do it. So I hope I answered all of your questions in that.
Okay, thank you.
Chen?
Yes. Very exciting talk. Thank you. So about your comment about this photon and polymer scattering to produce rho zero, then rho zero to pi plus and pi minus. You said that there difference between the two different parts, but why can you say so? As I understand, maybe there's a interference between two pions, for example, 2 pi plus from two different nuclei. So this is pi plus, and interfere with pi plus, and the pi minus interfere with pi minus.
Yeah, so I was going a little bit quickly at this point. So let me try to clarify and then tell me if I'm answering your question. So these are ultra-peripheral collisions, and we're only producing one real particle, one real row, which decays to a single pair.
Either from this or that.
And so in the final state, we have 1 pi plus and 1 pi minus.
Yes.
So I just want to clarify, we don't have multiple, so we can't have an interference like HBT effect, where you have multiple pi pluses, interfere, or multiple pi minuses interfere. In the final state, we have 1 pi plus and 1 pi minus. So that's one clarification.
But this pi plus, for example, can be from this nucleus or that nucleus, but they can interfere, right?
Yes, and I think what you're saying is essentially this picture. So, or maybe this picture is the better case. So, indeed, what we have in this case is at the amplitude level or at the wave function level, we have a row which decays to a pi plus pi minus on the left.
Yes.
And on the right, we have a row which decays to a pi plus pi minus. And you're exactly right. in standard quantum mechanics, you have interference between the pi plus wave function on the right and the pi plus wave function on the left. I think that's what you're saying. I completely agree with you. The distinction, though, is that this is at the wave function level. At some point, the pi plus and the pi minus wave functions have to combine or collapse, whatever you say, into these real particles. And at that point, this interference that's purely between the pi plus and the pi plus, there's no observable that's sensitive to that. That's really just purely the phase of these waves. What we end up observing with this phi angle is an interference between the pi plus and the pi minus. And the point here is that, so what you're saying takes place. You definitely have interference between the pi plus and the pi plus, and the pi minus and the pi minus. That definitely takes place. The question is, how does that interference get transferred between the pi plus and the pi minus in the final state real particles? So there has to be an extra step after these, wave functions interfere. There has to be an extra step to get it all the way into the final state. Does that make sense?
So Chen, these two are at long distance. They don't have correlation between each other, so their phases are random. Why would they actually interfere and result in a observable?
But you cannot distinguish which the rho zero comes from which nucleus.
Yeah, but their phase is random. So go back to the double slit experiment, right? Daniel, can you go back to the, So if I have two electron guns shooting through these two slits separately, you won't see interference pattern because these two electron guns, their phases are completely random to each other. Right? So these two wave functions, they don't know each other.
I see.
Right? One, for example, the interference is possible because the electron gun shooting, there is a possibility going to both slits. So their phases are fixed between these two wave functions. But if I'm shooting separately two electron guns at two slits, randomly, there will be no interference at all because the phase average out to 0. There is no interference. The cross term is always 0 because the phase is random.
I see your point. Yeah.
But this is a very classical experiment. You can actually do it with light as well, right?
Right. And that, so exactly, I think the way Jungbu explained it is really helpful, because that's why in this little section, there has to be some entanglement responsible for locking these phases together. Because as Jungbu said, if the phase is random, you end up with no, you average out the interference. So there's no interference in the end. So there has to be some entanglement somewhere to lock these phases and produce the interference pattern. And that's why I walk through, there's a few different possibilities here. One is that the entanglement just comes from the decay, because we know particle decay tends to produce entanglement. The other one is this kind of quantum teleportation idea, which is, it's a little bit crazy, but maybe there's some connection there. And then the third one, maybe if we go back to this, is that it's the same picture here. It's just that the rows are already entangled due to something happening inside the nuclei. So the rows are already entangled, and therefore everything beyond that is entangled if you start out in this highly entangled state. So you're absolutely right. There has to be some interference taking place, but you need that extra piece of the puzzle to lock these phases together. Otherwise, you won't observe anything in the end.
Oh, thank you.
Any other questions or comments? We still have maybe a few minutes. Okay, and that's pretty good. So Ian, anything else we need to do here?
No, but yeah, thank you everyone for coming, and we will continue for the next week.
Thank you for a very nice talk.
Yeah, and thank you.
Thank you.
Yeah, thank you,
Thanks,
Zhang Bu.
Danny,
Thank you.
again.
And great. Okay.
Good. Thank you, everyone.
Okay. Okay.
Bye.
Bye.
Bye-bye.